Welcome to the third video in our series. This is all about hardware, because one of the good things that you need to know is it's a good thing to understand how your programs execute. So before we actually get into talking about programming, I want to talk a little bit about how the hardware is organized. So we'll look at three different things. We'll look at how the machine is actually designed, which is known as its architecture. We'll talk a little bit about how the central processing unit works, and then how the memory is organized. And with those three things, we'll have a pretty good idea about how your Java programs are going to execute. In fact, any kind of program. Okay. Most modern computers, nearly all of them in fact, follow what's known as a von Neumann architecture. John von Neumann was a mathematician, a logician, a statistician, a game theorist. He did all sorts of things. In the early 1950s, he helped design a computer at Princeton University. And his memo on how the architecture should work is a classic document in computer science, and it's this design that pretty much everybody has followed since then. In a von Neumann architecture, the computer is divided up into 5 different areas. There's the central processing unit that we'll talk more about. There's input devices like keyboards and mice, output devices like displays and printers, auxiliary storage like your hard disk or flash drives or CDs, things like that, and then a main memory unit that directly talks to the CPU. Von Neumann's model is the basis for what's known as the stored program concept. In von Neumann's idea, all of the data and the programs are both stored in the main memory of the machine, and they are stored in exactly the same way. And the way that your program executes has how the CPU interprets what it receives from the memory, whether it's data or whether it's program. So the simple way of looking at the von Neumann architecture is it's all just bits in the memory. An alternative, this is the modern alternative to the von Neumann architecture. If you notice here, the von Neumann architecture, everything connects directly to the CPU. And that turns out is very inefficient. So what modern machines do is they have what's called a system bus that connects the CPU and the main memory together, but then all of the other devices are also connected via a different bus. And a bus is just a group of wires that connect the different devices. What this does is it allows the devices to do things simultaneously, so that you can be reading something from the disk into the CPU. You can actually, in a modern computer, read it directly into main memory at the same time that you're printing something out. And so this is a much more efficient way of organizing the architecture. But you still have the same 5 basic pieces. Okay. Hardware. Actually, just looking at computer hardware is pretty boring because everything that is important to us is too small to see. The only really interesting pieces in terms of visual acuity or whatever are the pieces that are electromechanical. Disk drives are electromechanical. They have this motor, which is called a stepper motor, that moves these arms across the head, the surface of the disk. These things out here are called the heads. These things move out and it reads the contents of the disk. At the end of the head here is a magnet, an electromagnet, and the surface of the disk is covered with iron oxide, and so you can magnetize it, and that's how it stores data. CPUs are boring on the outside because this is basically all you ever see because everything is too small. All right, so speaking of CPUs, how does the computer actually work? Well, the first thing to remember is that the computer is stupid. Okay? It actually only can do a very limited number of things, and it can only do whatever you tell it. And it does exactly what you tell it to do, nothing more, nothing less. So that's the sort of stupidity part. It's not very good at interpreting and doing what you meant to do. So all the computer really does is this. It loads data and instructions from the memory into the CPU. It decodes the instructions, and then it executes them on the data that it's loaded. And then it saves the answer back to the memory. Maybe. Sometimes it doesn't. There are some instructions that don't save anything. And that's actually it. That's all it does. And then it goes back and it does this again and again and again and again and again. This is known as the fetch-execute cycle of a computer. And this is what every single computer, the one in your phone, the one in your car, the one on your desk, they all do the same thing. They load the data, they decode and the instructions. They decode it, they execute it, they save the answer, and do it all again. So how can the computer do all of these really cool, fancy things? Well, the thing is, it does it really, really, really fast. The computer that I'm using right now, the computer you're reading this on, executes the fetch-execute cycle somewhere around 2 billion times per second. So even though the computer can only do small things and it can only do simple things, it's the combination of all of those things that it can do hundreds of millions and billions of times that allows it to do very complex and complicated things. And this all depends on the fetch-execute cycle. So that's how your computer works, period. In the stored program model, the instructions and the data, as we've said, are stored in the computer's memory. They're represented in the same way. And so how are they represented and how does this happen? It's that on-off thing. It turns out that on-off switches are very easy to make. A transistor. A single transistor is an on-off switch. At a certain level of electrical current flow, it will inhibit the flow of electricity. You raise the flow of electricity just a little bit and it switches and it allows electricity to flow through it. So transistors are switches. And that's what everything is pretty much based on. So all of these things have two different states, on and off. So all modern computers use binary, the binary number system, to represent all kinds of data and instructions. And it's all about the patterns that you can form when you put a lot of different binary digits together. So, danger, obligatory math content approaching. Okay. So to count, we use a positional number system. You learned how to count in decimal. Decimal is a positional number system. Positional number systems use some number of symbols, and they have a base that they work on, and the base is equal to the number of symbols that you use. And the value of each symbol depends on the position of that symbol in the number. So if I have a number 357, for example, the 3 in that number is in the hundreds place, so the 3 means 300 in that number. But if I use the number 34, then there's still a 3, but the 3 is now in the tens place, so it means 3 times 10, or 30. So the symbol 3 can mean different things based on the position it is in the number. And so at decimal, we have 10 symbols, 0 through 9. But that's too many things, and our switches don't work that way, so we use binary. Binary just has 2 symbols, 0 and 1. A single binary digit is called a bit. It's short for binary digit. And it's all about, the way your computer works is all about the patterns of those binary digits. There's a really nice video produced by Harvard out on YouTube. You should just click on this link and go to that video and watch it. It's about 8 or so minutes long, and it gives you a really good introduction to binary and binary counting and everything. I'll wait. Okay, now that you're back and you've watched the video and you know all about binary now, we'll talk about representing other things than numbers. Because, of course, you don't typically use a computer just to do arithmetic, right? It's not just a calculator. It's much more than a calculator. You use a computer to read things. You use a computer to listen to music. You use a computer to watch videos. You use a computer to surf the internet. And so in order for you to get information from the computer, it has to display it in such a way that you can understand it. And you're not going to understand long strings of zeros and ones. So let's just focus on text for a minute. We'd like to represent in text, we'd like to represent things like letters, right? So what they did in the very early days of computing was they said, let's create a set of codes that will map a particular pattern of bits into a particular letter. And one of the early versions of these codes is called ASCII. It stands for the American Standard Code for Information Interchange. It's very US-centric. It is a 7-bit code, so there are 2 to the 7th different patterns, or 128 patterns, running from 0 to 127, as you can see in this chart. In this chart, the left-hand column here, these 32 ASCII characters are known as the non-printable characters. They're things like backspace, ring the bell, line feed, tab, actually horizontal tab is up here, vertical tab is here, form feed, carriage return, all sorts of stuff. These are also stuff to control communications devices. The other 96 characters are what are known as the printable ASCII characters, and they contain a bunch of punctuation, they contain the number digits, and they contain the Roman alphabet, upper and lower case. And this is what pretty much every computer still recognizes. Every computer will still recognize the ASCII character set. And so when your display is trying to display a page of text, it sees these different patterns, and the display itself converts the pattern into something on the screen that looks like, say, a D, or a Q, or a 3, or a plus sign. And you don't have to worry about that at all. It just happens because it's built into the display. But the problem is, we'll come back to that. The problem is that ASCII is very limiting. It doesn't, for example, take into account any of the accented characters that any of the other Romance languages use. So it doesn't have the accent aigu and accent grave from French. It doesn't have an umlaut for German. And of course, it certainly doesn't look at any other alphabet. So what they did in the 80s was they decided, well, this is stupid. We should universalize this language. And so they created a universal code called Unicode. And instead of just using 7 bits the way ASCII does, Unicode uses 16 bits. So there are 2 to the 16th, or 65,536 different patterns in Unicode. And that way, you can have the Roman alphabet, but you can also have the Hebrew alphabet, you can have the Greek alphabet, you can have 2 different kinds of Chinese, you can have Korean, you can have the Russian Cyrillic alphabet. There's all sorts of stuff in there. And there's actually still plenty of space left over. But with Unicode, then we've universalized the representation of text so that you can switch your computer to just do Cyrillic. And so, but it's all still just patterns of bits inside. We've just expanded the length of the pattern. Okay, lastly then, we'll talk about the memory hierarchy. Back at the beginning, when we talked about the CPU, we saw that the CPU had three different pieces in it. There was a control unit, there was an arithmetic unit, which the arithmetic, the control unit is the brains of the outfit. It does the interpretation of all the instructions. And then there was this thing called registers in the middle, and those are small pieces of memory that will hold intermediate results when the CPU is doing calculations. And it turns out memory's expensive. And so what we have to do is, you can't afford to have an entire computer made of just registers because it would be too expensive. Your little $700 laptop would be about a $70,000 laptop if you had 32 gigabytes worth of registers in your computer. So we've created this hierarchy so that we can communicate as quickly as possible, because the CPU runs faster than any memory that you know. And so that's why we want to get memory close to the CPU to be very fast, and memory that's further away can be slower. So the registers are the smallest amount of memory that you have in your computer. They're small, but they're the fastest. They're almost as fast as the CPU itself, but they're very expensive. So there's a slightly slower version called a cache memory. You typically have 2 or 3 levels of cache memory in your computer. Some of it is on the CPU chip, some of it is off the CPU chip on a separate chip. And those are slower than the registers, but they're faster than the main memory. They're less expensive than registers, but they're more expensive than main memory. Main memory is still pretty fast, but it's much slower than the registers or the cache, like an order of magnitude slower. But it's cheaper. Your computer, your laptop computer, probably has at least 8 gigabytes of main memory, and some of you may have 16 or 32 gigabytes worth of main memory. And so that's good, because the more memory you have, the faster your stuff is going to run. Then another order of magnitude or 2 slower is magnetic disks. Magnetic disks are slower because they're electromechanical, and it's the mechanical part that slows them down. Sort of in between main memory and disks are flash memory sticks, just the little sticks that you poke into your USB ports. They're slower than main memory, but they're generally faster than a magnetic disk. If you have a computer that has SSD memory, solid state device memory, that's another form of flash memory. Your phones have SSD memory, so your phone has flash, your smartphone has flash in it. And then finally, the slowest ones, big, slow, but very, very cheap, is magnetic tape, which hardly anybody sees these days because they really only use it for backup. And then different kinds of optical discs, CDs, DVDs, Blu-ray, optical disc. And these are yet another order of magnitude slower than even the magnetic discs. But they're cheap because they're plastic, and they can hold a lot of data. And so that's the hierarchy. You actually want as much of the memory up here as you can get, but it's a cost-benefit trade-off because more of this is more expensive than more of this. Okay, and that's pretty much it. That's it for the, oh, well, I guess we'll talk, of course. Sorry, forgot about memory. The way memory is organized is it's a list of cells. And each one of those things has a unique physical address. Memory is addressed starting at address number 0 and goes all the way down to however long it is. It's usually some power of 2. There are 8 bits to a byte. 1, 2, 3, 4, 5, 6, 7, 8 bits to 1 byte, and the machines are byte addressable, so you can your program can access a single byte of memory of the main memory. But main memory is also grouped together into things called words, and this is how big a register is. The definition of a word for any computer is how big is a register in the CPU. Most computers these days, including the ones you have, are 64-bit words, or 8 bytes to a word. 8 times 8 is 64. So you would have one machine word is these first 8 bytes right here. Oops, 0 through 7, not 0 through 8, John. That's a machine word. And whenever you want something from, whenever the CPU wants something from memory, you get it in multiples of machine words. Even though you're byte addressed, even if you want only a single byte, you're going to get a whole word. Because it's just more efficient to do the transfers that way. If you take CS201 or CS226, you'll get a lot more of this stuff. So, where do we go from here? Well, so the computer is the tool that we use to solve the problems. We need to learn to use the tool to solve the problem. So the computer is like our hammer, right? And our saw and our drill if we were a carpenter. It's a tool that we use, but in order to become a good carpenter, we have to learn how to use the tool, and how do you learn to use the tool correctly? And for us, the skill that you need to learn to use the tool is programming. And that's where we're going next. And now we really are done. Thanks.